Good afternoon and welcome to today's webinar, Decarbonizing Thermal Applications for a Sustainable Future. My name is AJ Piskor. I'm the Combustion and Advanced Controls Business Development Manager for Lesman Instrument Company and your host for this webinar. Today we have two speakers joining us today. We've got Brian Kelly and Todd Ellerton. They are both with Honeywell Thermal Solutions. Brian actually came through Honeywell via Hauck Manufacturing. And Todd Ellerton came through Honeywell via Eclipse, all now part of Honeywell Thermal Solutions. So today we are going to be talking about different aspects of decarbonizing, and Brian and Todd will trade off between different topics. I do invite you that are attending live that if you do have any questions, please post your questions in the chat. I will get Todd and Brian's attention as it allows, or if you wanted to wait to the end of the presentation, that's also a great time where we can have a little bit of Q&A with our presenters. So having said that, I'll turn it over to Todd.
Great. Thanks for that intro, AJ. Brian and I appreciate the opportunity, and we're excited to be here with everyone today. So let's jump in. So what does sustainability mean to you? I don't know if anybody out there has really stopped to think about that. It means slightly different things to different people, but thought maybe we'd start with the definition of sustainability. Here are a couple of more formal definitions of sustainability. The first one is the ability to be maintained at a certain rate or level. The second one, avoidance of the depletion of natural resources in order to maintain an ecological balance. So slightly different takes on sustainability. But there's kind of three principles if we zoom out a little bit and think of sustainability more holistically. There are kind of three core concepts: environmental, social, and economic. Also sometimes referred to as people, planet, and profit. So in this broader view, a business is considered sustainable if it can conserve natural resources, support a healthy community and workforce, and also, and very important, earn enough revenue to remain viable, for the long term. So with that, there's growing focus on carbon reduction as it relates to sustainability, the environmental aspect of sustainability. And there's growing focus on carbon reduction because of climate change. This is a view of carbon emissions over time, starting about 1850, through the Industrial Revolution, through today, and projection of where things will eventually end up if we do nothing. And as I mentioned, all the negative impacts that can come along with that. So there's certainly efforts being taken to reduce carbon emissions. There's a growing focus to address those things. Started back in 2005 with the Kyoto Protocol. Really came to a head in 2015 with the UN Paris Climate Accord that established a legally binding treaty to try to limit global warming to below 2 degrees Celsius, with really an ambitious target to limit it to 1.5 degrees Celsius. And beyond these UN accords and COP conferences, governments are enacting things like carbon taxes and NOx regulations to try to improve the environment and stop global warming. The NOx is not so much related to global warming, but more of a health factor there. And in addition to these, say, sticks with the regulations and penalties, there are incentives also being established to span things like renewable power and hydrogen. Examples of those are the Industrial Green Deal in the EU and the Inflation Reduction Act, or IRA, here in the US. And lastly, many corporations themselves are taking action and making commitments to reduce their carbon footprint. This is typically done by working with an entity like SBTI, which stands for Science-Based Target Initiatives. They act as a kind of a third-party scorekeeper on those greenhouse gas reduction commitments. And the chart at the lower right just shows how there's a definite growing trend in the number of or the quantity of emissions that are falling under the coverage of SBTI. And you can see there was a kind of a marked increase. It's hard to make out the dates, I know, at the very bottom, but around 2019, there was a marked increase in escalation in the rate of emissions falling under their kind of purview. So what is carbon footprint? Well, it's more than just CO2. So there's 6 gases or families of gases referred to as greenhouse gases. They're shown here. So it's carbon dioxide, methane, nitrous oxide, halogenated gases, etc. And they each have a global warming potential, which is how much heat each gas traps relative to CO2. So if we take a look at methane, it traps about 25 times the amount of heat as the same volume of carbon dioxide. This last chart here shows kind of the relative impact on climate change of each of the different greenhouse gases. So even though methane is 25 times worse, it's only having about 16% of the impact. Similarly, where fluorinated gases are thousands to tens of thousands times worse per unit volume, there's just so much less volume that their overall impact is much less. Carbon dioxide, as you can see, is about 3/4 of having about 3/4 of the impact on the climate, and that's why CO2 is kind of the top priority. But we are seeing more and more focus on methane as that kind of number 2 greenhouse gas. And then CO2e, or carbon dioxide equivalent, is something you may have seen. This is a measure of total greenhouse gases emitted expressed in terms of the equivalent amount of CO2. So 1 ton of methane, for instance, would be expressed as 25 tons of CO2e. So taking a look at where folks on this call likely play in industry, and specifically industry or industrial process heat, we can see that industry is responsible for about 30% of global carbon dioxide emissions and about 33% of methane emissions. Now on the methane side, the majority of that's going to be in the oil and gas production side and the distribution of natural gas. So not so much in let's say the industrial heating space that most of us play in. So the focus for us is really going to be on CO2. And so industry, as the title shows here, certainly has a big role to play in carbon reduction. So another definition here, since industry is such a big emitter of carbon dioxide, it will need to decarbonize. We have another piece here. Decarbonization is the process of removing or reducing the CO2 output of a country's economy. This could be thought of in terms of a company as well, not just a country. So CO2 reduction, how can industry go about decarbonizing? There are actually quite a few things that can be done to reduce industrial carbon emissions. The first is using alternatives to fossil-based fuels. So we could go to electric heating. We could use power to methane, which results in methane but not fossil-based. We could use hydrogen. We could use biogases and biofuels. There's also a lot that we can do in the area of improving efficiency. We can deploy heat recovery. We can use better air-fuel ratio controls. We can, better tune our combustion equipment, make sure it's running at its optimal settings. So those are all things that can be done. And so at this point, I'll turn it over to Brian. He'll dive into alternatives or renewable fuels.
Good afternoon. So when we talk about renewable fuels, those are fuels that can help reduce or eliminate carbon emissions. There's been talk about ammonia because of its high hydrogen content and a more stable carrier and easier to transport maybe than liquid hydrogen. Of course, there's hydrogen, which has gotten a lot of press and can be very useful, obviously, and we'll talk about that a little more in depth here in the next few slides. You've got methanol, various biogases, right? We run into a lot of people on the application side that are looking to burn waste fuels, syngases, off gases that can help them reduce that fossil fuel or that carbon-based fuel content. And then also the availability of renewable natural gas. So taking sources that can be turned into natural gas that don't have that carbon. But what we see is that hydrogen in many industries is expected to play a pretty key role in the reduction of CO2 from industry. So I've got a pretty busy slide here, so I'll go through this pretty methodically. So when we look at hydrogen and its role in possible carbon reduction is in a simplistic combustion formula. When you look at the natural gas, treating natural gas as methane, CH4. When we look at combustion, I'm ignoring the nitrogen in the air, but when we look at the base result of combusting methane in oxygen atmosphere, the result is CO2, water vapor, and the energy that results right now, methane, natural gas, is about 1,000 BTUs a cubic foot. Obviously, the carbon in the methane combines with the oxygen, we get our carbon dioxide. When we look at hydrogen to offset that natural gas or a carbon-based fuel, you'll see those two parts of hydrogen combine with oxygen to make water vapor and energy. So we eliminate the CO2 because we no longer have any carbon within the fuel base to convert. So when the hydrogen possibly produced with renewable energy, hydrogen as an energy carrier results in a CO2 neutral energy form. And we'll talk about that a little more in terms of the production of hydrogen. But when we look at from being a combustion guy, when we look at the combustion characteristics of hydrogen, hydrogen's number one on the periodic table. It is the lightest and smallest element in the periodic table, which means that when we start looking at a fuel-based, a gas-based hydrogen combustion system, we need to pay attention to possibly leakage rates through control valves, shutoff valves, things of that nature that we obviously look at now for natural gas, propane, those type of fuels. Being a smaller molecule, it may have an increased leakage rate. And there's been studies, and we'll talk about that in a couple slides here. Hydrogen is colorless, odorless, tasteless. Just like we warn about CO2. CO2, obviously, that's deadly because of its constituents. Hydrogen, where natural gas has mercaptan for a smell, they're working on an odorant for hydrogen as well. And because that's some of the main concern is if it does leak, we can't detect it right now. But being 8 times lighter than natural gas at 2 grams per mole versus just base it on methane at about 16 grams per mole, it's 18 times lighter. So if it does leak, it's going right up. So much less dense, and we'll talk about that a little bit. Hydrogen is easily ignited. It's 15 times lower spark energy required to ignite hydrogen than natural gas, which it makes it a great fuel source. It's been a fuel source for for a long time in the typical places we find hydrogen are in refineries. So they've used that as a fuel base just because it is a byproduct of some of the processes they do. The flame burns plus or minus 8 times faster than natural gas. So our flame speed's much higher than natural gas. And it can vary from 5 to 6 to 8 times faster, depending on the type of mixing. It burns a little faster in laminar flow than non-laminar. But from a combustion side of it and burner side of it, and we'll talk about that in a little bit, it can pose some challenges in the traditional natural gas or carbon-based fuels. Hydrogen does have a higher flame temperature than natural gas, about 400 degrees Fahrenheit, so we need to be concerned about materials of construction and things of that nature. Coming back to the flammability, the lower spark energy to ignite it, extremely flammable. Your lower to upper explosive limit of hydrogen is 4 to 77% by volume in air. Natural gas, methane is about 5 to 17, 18%. So you can see if you've got a little hydrogen in your fuel, it's going to be a very, very useful and very flexible fuel source in terms of its ability to combust. When you look on a volume basis of the heating, the value factor of natural gas, it's about 325 BTUs per standard cubic foot, higher heating value, about 290, lower heating value. So that's 3.5 times lower than most commercial natural gases. So roughly you're going to need 3 times the volume of hydrogen to get the same BTU out of your system than natural gas. And we'll talk about that result in the next slide. But our graph in the lower right here is looking at the hydrogen content and its result of the hydrogen part of the total heating value of the fuel. Because you might say, because there's been a lot of talk about boosting or blending hydrogen into the natural gas grid into different processes to reduce carbon. The less natural gas is the less carbon in the fuel. But what this graph is showing is it's not a linear function, in that if your hydrogen content is, if your hydrogen blend in natural gas is 50% per se, say, if you take that line up to our curve there, you're looking at about 24% of the total heating value. So really what this graph means is when you've got a 50-50 hydrogen natural gas blend, you're reducing your CO2 by about 23%. So if you go and look at that on the upper scale there, that 50%, you're up at about 78% hydrogen and natural gas to get a 50% reduction in your CO2 as a result of combustion. So and that is that's just physics, right? That is going to the much lower density, the specific gravity, which is the density of the natural gas versus the base air, is about roughly 0.6 specific gravity. The specific gravity of hydrogen is about 0.07. So it's much lighter than natural gas. That's why this graph looks like it does, because of those characteristics. So when we look at hydrogen, I've got a pretty busy graph going over here on the right, but I'll try to simplify it. If the burner's capable of burning hydrogen with no changes, the required gas pressure at the burner will be higher with hydrogen, whether it's pure hydrogen or as a mix, than the natural gas to achieve that same capacity. So say 1 million BTUs an hour. You're going to need 3 times the amount of hydrogen, roughly, than the natural gas. What our graph here on the right side here is showing is simplistic. If we look at the fuel flow is the purple line there. That's just exponentially going up, and that's just showing your increase in fuel flow required as your hydrogen content increases. So when you look at that 100% line, you're looking at about 3 to 3.4 times the amount of fuel or flow for hydrogen than natural gas. Pretty much what we were saying, 3 to 3.5 times. The dotted red or the dashed red line is the fuel pressure And you might say, hey, what's going on here with this kind of little waterfall at about 85%? And that's a function of really the Wobbe index. It's a combination of the fuel value, the change in fuel value as our hydrogen natural gas blend increases in hydrogen, the heating value goes down. But also our specific gravity is the Wobbe index is a square root value. I'm not trying to get too technical here, but that's what's affecting our pressure. But in the end, if you look at where that dashed red line lands over on the left vertical line there, it's relatively flow and pressure percentages, you'll see it about 130% off 100, so about 30% increase in pressure required, staying with the same burner, the same orifice. Now, that may change depending on our type of burner and things like that. On the other hand, if you look at the light blue line, that's our stoichiometric air for the same lower heating value reference as natural gas. So as you can see with our increase in hydrogen in the natural gas, by the time we get to 100% hydrogen, we're at about 85% of the required air for stoichiometric combustion, so ratio combustion with hydrogen versus natural gas, which you might say, hey, that doesn't make any sense. I'm burning 3 times the amount of hydrogen. Well, it's also lower in heat content, and the theoretical air fuel ratio goes down to combust that because of the physics of the fuel versus the air and that combination. And then the air pressure is lower because of square root and the fluid dynamics. So you may be looking at 70%. So it really is important to consider that, and we won't get into it today, but when you start looking at blending and changes in natural gas and hydrogen blends, or even pure hydrogen, the type of application that you apply your burners to. We've got them all, right? We put heat into everything almost in the world, so from low to high temperature, and it really will dictate possibly how the burner gets controlled if a tight air fuel ratio is required in a higher temperature application to prevent metal loss, or you're just heating air and air fuel ratio doesn't really matter. So, and in some instances. So when we talk about emissions, so burner mixing design influences the impact that hydrogen has on NOx emissions. Actually, some burner mixing designs will not work with hydrogen at all, or not work well. For example, premix. Premix was developed a long time ago. Well, if you're familiar with premix systems, you're mixing the air and what generally is natural gas now for a flammable mixture, and that your turn down is about 4 or 5 to 1 until you start flashing back, because you've got that flammable mixture. Your velocity isn't enough to maintain it on the burner nozzle, and it burns back or flashes back. Well, you can imagine that when we said the flame speed is 7 or 8 times higher with hydrogen and natural gas, premix becomes a very difficult type of combustion to maintain, and especially get turned down. Some burners use high excess air and spin and partial premix to reduce NOx. And some of our burner technologies at Honeywell certainly use that. That doesn't play well with hydrogen. So we've been doing a lot of testing over the last 3 or 4 years to really identify what works and what works well. What do we need to start concentrating on to look at lower NOx emission burners on hydrogen? What we've seen in a lot of our testing is a notable shift in NOx levels. You'll see increases in NOx levels, and it varies depending on the burner design, but generally we'll see a notable shift in NOx levels start increasing significantly above 70%. And that's to a scale depending on the burner. But something to note here is so many of our, you go to California, and so many of our inquiries from customers that require low emissions burners are generally saying, hey, we need below X ppm, reference to 3% oxygen. We really say that should be avoided in hydrogen, and really should go to a mass per unit energy is preferred to compare NOx from natural gas to hydrogen, because when you look at, say, natural gas, treating as methane, by volumetric, 50 ppm at 3% O2 reading translates to about 0.06 pounds per million. If you look at that same 50 ppm based on hydrogen, on a mass basis on pounds per million, it translates to 0.041 pounds per million. So you can see that if we go ahead and even that volumetric measurement of hydrogen back up to equal to that 0.06 pounds per million, you're looking at a volumetric measurement of 73 ppm at 3% O2. And that comes really from your less volume of your POCs. You'll require less volumetric stoichiometric air. And the physics make that change pretty significant. So this is something that in the future, I'm hoping, because this is always, this always goes to contention, right? Because in most burners, NOx goes up as you turn the burner down, some more significantly than others, depending on the type of burner and its intended application. But your pounds per million, as your firing rate goes down, your mass is going down. So it really should come down to, hey, what are you actually releasing into the atmosphere? So this is it's a tightrope that we are on sometimes. So it'll be interesting to see where the industry goes in terms of measurement of NOx and how we record that. And hydrogen in industry. So when we look at the benefits and outlooks, right? So hydrogen, when hydrogen produced with a renewable energy source, say your renewable sources, your wind, your solar, hydro, if it's produced with a renewable energy source, it's going to result in a CO2 neutral energy source, so green hydrogen. So we can work our way, look at the left side here, gray hydrogen. That's really from your SMRs, your steam methane reforming, which is the majority of it, 98%. Most of that is done in your refineries today. So they're going in and cracking natural gas and getting the hydrogen as a byproduct out of it and burning it. And as a result, guess what? That CO2 right now with gray hydrogen is still expelled into the atmosphere. So we don't have a CO2 neutral hydrogen source. It's got a CO2 footprint to it. We do get hydrogen out of it. As we progress and look at, hey, oh, well, where do we go from here? So look at the production of blue hydrogen. Still that same process with the natural gas, but we're no longer expelling that CO2 into the atmosphere. We are somewhere sequestering it or doing carbon capture and storage, whether it's underground storage, things of that nature, to prevent that CO2 from entering the atmosphere and being harmful. And then we're looking at some timelines here on what's realistic, right? And that's going to shift. So when we talk about that green hydrogen, we're looking at electrolyzers that are going to take water in and produce hydrogen and oxygen, actually. But that's got to be done with green or renewable energy. So we've got a green or power source that does not have a carbon footprint that can't be associated with that hydrogen. So that's what we talk about green hydrogen. It truly is a green source that takes water in and we produce oxygen and hydrogen out of it. And that's over on the right. There's that hydrogen going to the natural gas grid, boosting maybe methane. CO2 can go through a catalyzer, but those sources are going to power generation, industrial or residential, and even cars, right? So that's going to work its way down through the industry. So some of the outlook has been talked about that Europe, Canada, as well as here in the US, pretty much all over the world, is the most economic ways to distribute that hydrogen is to possibly mix it in the existing gas grid. Right now, some people say 20%, 25%. We've seen a consensus kind of blending up to 17% hydrogen will be acceptable without changes to the distribution network and maybe only minimal changes to most appliances. That being household furnaces, stoves, commercial boilers, some of our industrial processes we have to look at depending on the type of burner. What we'll see is probably, you may have already seen it, local, small scale hydrogen distribution can go up to 100%. Some people will make their own. There's companies that are selling electrolyzers right now, and they can be limited in capacity, right? So your larger users of natural gas and those carbon-based fuels will need to look at that as what is their source, and do they have sources to be able to produce that hydrogen locally with a renewable energy source. So it's certainly long-term higher levels up to 100% are going to be targeted, but that's going to take time to achieve, just like anything. But that promise, or that availability of green hydrogen in the future, is going to look to try to get to that zero carbon footprint.
Right, and just to add to that quickly, I mentioned the
Yep.
IRA, or the Inflation Reduction
Yep.
Act, earlier. Yeah, so that's going towards establishing some of the first, more local or regional hydrogen distribution systems. So, what has HTS been working on related to hydrogen here of late? Brian mentioned 3 or 4 years ago, we started really doing a lot of testing. We've worked with hydrogen-based fuels for decades, things like coke oven gas and town gas, but 100% hydrogen is something we didn't see a lot in the past. So we started putting our burner portfolio through a battery of tests at our labs here in the U.S. and in Europe and Germany and Belgium, to see how they performed with really different blends of hydrogen with natural gas. And here's a series of photos with one of our burners, starting with 100% natural gas on the left, progressing up to 100% hydrogen on the right. You can see even with 80% hydrogen, the flame is still, in large part, very much looks like a natural gas flame. It's got that distinctive blue color, pretty opaque flame. But once you cross over 95, 100% hydrogen, for sure you get this more reddish orange flame. It's a bit more translucent. It's not as visible to the naked eye, for sure. Fortunately, it's still very visible with UV flame scanners. Took a similar approach with our fuel delivery components, starting with material suitability, making sure that the materials of construction were compatible with 100% hydrogen, and then moving on to functional behaviors like flow rates and leakage rates and so on. And we've been going through our portfolio, documenting everything and putting it into our worldwide certification list. So this document is available in our DocuTech literature repository. It's available online. So this has historically been used to display what certifications our different components carry, things like CE and UL. But we've added hydrogen capability. You can see in the far right hand of this image, we've added hydrogen capability to this document at different levels: 10% hydrogen with natural gas, 30%, 50%, and then 100% hydrogen. So this is available to anyone. You can take a look and see what valves, what burners, et cetera, are available for different blends of hydrogen. And to this point, what we've found is we've got a wide range of hydrogen capable burners. It's somewhere on the order of 26 or 28 different burner families that are capable of working with at least 30% hydrogen in a natural gas blend. Many of those are capable up to 100%, but as Brian mentioned, it really depends on the burner design, its mixing characteristics, et cetera, on how well it works with hydrogen. So, and there's a number of burners that we haven't had a chance to test yet. So that work continues, and that worldwide certification list is a living document. We're constantly making updates there. So something that may have shown, something last year could be changed and show hydrogen capable, later this year. And then on the fuel delivery and burner management side, what we found is the vast majority of our components are ready to go for 100% hydrogen. 95% plus, I would say, from our shutoff valves, control valves, pressure switches, mentioned flame scanners, et cetera. So combination of this basically means we've got a solution available for virtually any application between the burners and the controls that we have. I got a couple of case studies to show. First one is a project that we did. We took the order, I think in 2022, delivered it in 23. This was for the paper industry, for a Yankee hood dryer, a couple of good-sized burners, 6.5 megawatts each. That's roughly 22 million BTU per hour each burner, set up to fire from 100% natural gas up to 100% hydrogen and variable blends in between. End user was concerned about efficiency, so the system's equipped with heat recovery to preheat the combustion air. It's a special implementation of our NP airflow line burner, 4-strap version, and so we provided the burner in a duct section as shown in this CAD model on the right. Gas train, fuel air ratio control system, the BMS, and Thermal IQ, which is our software remote monitoring and optimization system. And then just lastly on this slide, the images in the lower right. So this is the type of burner that is in the system. It's a line burner shown firing natural gas here on the left and hydrogen on the right, so you can see the very different flame characteristics and color between the two. Next is another case study. This was for a combined heat and power system actually in Belgium. We originally sold a turbine exhaust gas reheat system, so HC airflow line burners for natural gas, and the end user came back to us. So that was sold in the 90s. The end user came back to us about 10 years later. So this is 15 years ago maybe. So it's been a while, but shows that we have some decent experience working with hydrogen. They had access to hydrogen. It was going to be variable though, so that one day they might have zero hydrogen available. The next day they might have plenty of hydrogen where they could run the system on 100% hydrogen. So the team developed a system to blend hydrogen into the natural gas, for whatever was available, and it was a very successful implementation of hydrogen into that system. And fortunately, the HC airflow is one of those burners that doesn't require any kind of modifications to work with hydrogen or natural gas. It's the same burner. So great story there. On this slide, just an overview of the many different tools and resources that we've assembled related to hydrogen. We've got a dedicated web page that you can access at this address here, thermalsolutions.com. honeywell.com/zero carbon. We've got a white paper, a technical brochure, which is kind of a, things to consider when working with hydrogen. The worldwide cert list I already covered. Different articles and webinars that we've done in the past. So those are available. If you're interested, we can help connect you. Most of these are available in our DocuTech or at this website. So with that, I'll turn it back over to Brian to dive further into efficiency.
Yeah, so right now, hydrogen looks to have a good future in reducing, if not eliminating, carbon dioxide or your carbon footprint, or reduce it at least. But what can we do in the meantime, right? Because if you look at improving your efficiency of your combustion system, of your operations, means you burn less fuel. Less fuel means less natural gas, I should say. Less carbon-based fuel means less carbon dioxide emissions, fewer carbon emissions. And as Todd had preluded, this isn't just burning a carbon-free fuel. This is a tighter air-fuel ratio, reclaiming some of that heat. It's like if you capture that waste heat, allows you to harness that thermal energy that would otherwise escape out the stack, escape other places, and put that to use in preheating combustion air or other places in processes. So sometimes that thermal energy doesn't necessarily have to go to the combustion system, but that's what we're going to concentrate on today, because that's our bread and butter. So just to say that Honeywell Thermal Solutions, we've got a portfolio that, with the combined companies that we've acquired over time, to help with that improved efficiency and waste heat recovery. So if you look at that, it's like, okay, heat recovery and recuperation, and we'll delve into that. So we've got that capability of burning more efficiently. But another part of that is, how about more precise fuel air ratio control? And that can vary depending on the application that you are using your combustion equipment in. But with the availability of more tighter control on actuators, tighter control of your air fuel ratio with more precise systems, you can tune in your burners to be more efficient and reduce that carbon today. And something that I can't stress enough is just routine inspection and maintenance. I've often been asked, is like, hey, how can we reduce the carbon? And I pretty much say, how about go tune your burner system and fix the holes in your furnace? That's pretty easy. But it's not to be taken lightly, right? Because things will drift over time. There's just no doubt about it. Things will change, things will wear. So take a look at that. And then also process monitoring, right? I mean, being able to monitor the key indicators that will indicate that your process is no longer operating at its optimum, right? So there's numerous products and systems available to reduce that carbon footprint. So go ahead, Todd.
Yep.
Heat recovery. Recovering that waste heat out of your ovens, your furnaces, your thermal process lets you capture that thermal energy and put it to work in the process. It's going to, again, improve that efficiency, which is going to reduce your fuel, or save you money in fuel, and then as a result, reduce carbon emissions. If you look at the rest of the world, natural gas fuel is very expensive. We are a little spoiled here in the U.S. is that our fuel is pretty cheap. But I think you're going to see more and more of the opportunities for heat recovery and for improving efficiency, not by only just reducing costs, because fuel costs have gone up, but also in that carbon reduction and that sustainability end of things. So most straightforward way to capture that exhaust heat is through some type of heat exchanger. And that's typically, we're going to be air to air, or not air to water, things of that nature. So we've got that heat exchanger design. Two medias, they're separated by a solid wall, a plate, or a tube, and the heat is exchanged between the two media, right? That hot exhaust gas that's coming out is going to be transferred to the colder combustion air coming in. And heat exchangers can be added to almost any industrial process. You're not going to find a boiler these days that doesn't have an economizer, right? So boilers for a long time have done that. Not so much on some of the industrial end of it. So The type of heat exchanger it is, the type of materials and configurations are really dependent on those application specifics. And you'll see that through a heat exchanger, through burners with recuperators, and we'll talk about that a little more. So another method of this is self-recuperative burners, or burners with plug-in recuperator systems. A little bit of a case study here. This is actually a furnace that you can see by the initial picture looks a little aged. This was a continuous furnace for bright annealing. It already had radiant tubes, so indirect fired U-tubes with recuperators. So they were trying to be more fuel efficient, but what the customer was experiencing in this case was they had high temperatures outside the furnace due to there was exposed sections of the radiant tube, the pilot. There were holes in the system. You can see that you can see some of the, when you see bright spots anywhere in a combustion system, you're going to have some pretty significant heat loss, and something's not being maintained correctly. So they were losing heat, thereby wasting fuel, obviously not operating at their optimum efficiency to have a lower CO2 emission. So they were also seeing hot spots, reduced tube life, so they had increased downtime due to frequency of tube changes and actual leakage between burners and recuperators. So that was another heat loss. So they decided to upgrade the furnace to do quite a few things: reduce maintenance, increase runtime and uptime, increase efficiency, and improve their tube life. So what was done in this case was a change in burners. And in this case, you can see the before and after there, a little bit cleaner, which we would hope so, right? This upgrade was a conversion from those U-tube burners to self-recuperative. These happen to be Eclipse SCR burners, single-ended radiant tube burners that are single-ended rather than the U-tube, and installed. And once installed, they increased production by 18%. Hot spots were removed just because of the design of an SCR burner. It has a much more even tube uniformity and temperature than a U-tube. And they saw about a 30% reduction in fuel usage. And a 30% reduction in natural gas usage directly translates to a reduction in CO2 emissions. That's pure physics. So just a little graph there was the red line was before the conversions and the green line was after. So wasn't rocket science, really just improved the control and the integrity of the system, and with improved technology. So when we start looking, we talk about recuperative burners. When the first ones there are the EcoMax LE, which was the result of many decades of familiarity with the EcoMax, which is the standard EcoMax. The EcoMax LE stands for low emissions. We've got best in class NOx emissions with about a 7% increase over the standard EcoMax. Applications for both the EcoMax LE, EcoMax, and the SCR are metals and heat treating. What are the features of the LE? It's self-recuperative, just like the EcoMax. Improved efficiency. What we did with the LE was we obtained a flameless mode. So we had a direct and an indirect possibility in those burners, both the EcoMax and LE. But what the LE does is goes into above all ignition temperature. We go into a flameless mode, which takes down our thermal NOx drastically. And both these EcoMax LE and EcoMax can be both fired indirectly in a tube or open fired in a furnace, in an open furnace atmosphere. And both can be fired in metallic or ceramic tubes, and both available in ceramic and metallic versions for lower and high temperatures. The SCR is a tried and true self-recuperative tube burner. It's internally insulated and also can be fired in metallic and ceramic outer tubes. And then we've got our TFB burner from the Eclipse legacy Eclipse brand, along with the BU, the Bayonet Ultra Recuperator, which can see efficiency improvements up to about 60%, maybe a little more. That's from maybe 40. The efficiency is all based on furnace temperature, but it's going to significantly take your efficiency up probably 20 to 25% over cold air firing. Applications for that are a multitude in metals. It can be lower temperature tempering and annealing to hardening, up to higher with galvanizing and even liquid heating sometimes, and up to over cold air fire burners up to 40% fuel savings, and improved temperature uniformity in the YouTube as well. And this is where we also look at, we won't get into it today, but also firing methods as well. Is how accurately are they maintaining their fuel ratio and doing things to prolong that tube life and maximize efficiency. When we look at our heat exchangers from the Exothermics brand, these are driven, you'll see a tubular, sinusoidal plate and dimple plate. The tubular is going to be from your low to high temperature. Tubular max out about 1500 to 1600 degrees, depending on tube construction. And then your sinusoidal plate is going to be the most effective in heat transfer just because of the design. The dimple plate is medium. It doesn't have the sinusoidal or the tight packing of the plates that the sinusoidal does, but the dimple plate's made for moderately dirty atmospheres to be more easily cleaned or not clog as often. Tubular are suited for actually pretty dirty atmospheres if required. We're always looking to be as clean as possible, right? But all of these offer the ability to recover that waste heat. And some of those return on investments doesn't mean you need to be in a 1800 degree furnace, right? You can be lower temperatures and still see what a type of air preheat that can be obtained to transfer either to the combustion system or possibly in another process in the customer's plant. And when we start looking at improving efficiencies beyond the preheating or the reclaiming of heat recovery, is start looking at air-fuel ratio. That ability to maintain a tighter air-fuel ratio throughout an operational range of that system is going to help increase efficiency, thereby reducing fuel. And the easiest way to do that is something like the air-fuel ratio control that's available in the Slate product line, as well as that doesn't work unless you have high precision actuators to eliminate variations in your set points, both for your air and gas. You can have the best air-fuel ratio, air and fuel curves in the world, but if your actuators have very little hysteresis and cannot be repeatable, then you may just kind of be going around in circles. So our product lines such as Slate and SmartLink MRV and the high precision, both DS and the LTA, the Slate actuators, give us the capability and the opportunity to hold much tighter air fuel ratios and be more efficient in the process. And just a little case study here, this was a situation where the customer had an old mechanical MRV. And you can see there on the blue on the right, their temperature response in terms of when they had heat demand and where their temperature was varying was plus or minus about 50 degrees. When we installed the old mechanical, or replaced the old mechanical MRV system with a SmartLink MRV, you can see we got that temperature variance down to something acceptable in the plus or minus probably 10 to 15 degree range. So something that saw a much tighter air fuel ratio control, and depending on their process and their conditions, it reported savings from anywhere from 5% to 25%, depending on the product they were running and temperatures they were running at. And with that, I think, AJ, we're done with the pre-canned part of the seminar.
All right. Great. Thank you, Brian. Thank you, Todd. I certainly learned a lot today, and I hope that you attending did as well. All right. So one of the questions that we have is, can you speak briefly to costs and availability of hydrogen, ag sector, LPG replacement?
Okay. Well, hydrogen relative to natural gas at today's prices is fairly expensive, on the order of 4 to 5 times price in terms of the amount of heat that you're going to get. Now, the point of these hydrogen hubs that the Department of Energy is funding is to try to drive that down. There's incentives that are being offered for green hydrogen producers, and their intention is to get close to parity in the next 10 years. So they look for that, 4 to 5x to get down to 1.2 to 1.5x, let's say, within the next 10 years. So it's going to take some time to build up that infrastructure and to get that at price parity. But there are incentives. There may be incentives for not just producers, but for users as well that could be taken advantage of to to offset that price differential. I'm sure there's more to come in the years ahead in that space, but specifically on ag and as an LPG replacement, I don't have a lot to offer there. Brian, I don't know if you have any thoughts.
Yeah, depending on the industry and which part of the ag industry. I mean, LPG is generally a little more expensive than natural gas, so maybe not as much of a price difference. But yeah, hydrogen right now, as you look at between the green or gray and green and blue, and those are going to vary per million, right? But as a replacement fuel source, I mean, LPG, depending on the type of burner and the system that they've applied, some systems don't, the change in burners, sometimes there are no change in the burner internals and firing between natural gas and propane. So that would have to be looked at on kind of a case basis to see what might, if anything, or what might need to change in terms of the structure of the system. Because if they are only firing on LPG, generally compared to natural gas, the piping is smaller because propane is about 2.5 times the heating value of natural gas. Where with natural gas piping, and although we have 3 times the volume of hydrogen for equal heat input through a burner, the lower density of the hydrogen, we might need a little more pressure, but generally about the same size piping can be used, but may not be the case with propane. So I can't make a blanket statement there, but it kind of has to be looked at on a kind of a case-by-case basis.
Maybe one other consideration would be the size of the storage tank for hydrogen. I imagine would be considerably larger than the LPG, comparable LPG.
Well, yeah, and hydrogen stored in a liquid form at much lower temperatures, right?
Yeah, if you're going to go liquid, then yeah, it's completely, completely different system. Yeah.
Matt Smith asks, is the H2 natural gas blend percentage by mass or volume?
That's by volume.
Volume.
Because actually, if you look at a mass heat per pound, hydrogen is by mass much higher in terms of its energy than natural gas. It's just because we're looking at hydrogen generally in a gaseous form because it boils at such a low temperature. That's why it's so much lighter. But yeah, all our percentages are delivering in a volumetric gas form.
All right, thank you, Brian. Jason asks, is hydrogen used for HVAC systems yet?
I can't say that I've seen it yet. Brian, you see more of the.
I have not either. Certainly, yes. Yeah. Our business is generally on the industrial side of it, so I have not been involved in any discussions on that. Certainly with them talking about enriching gas grids, that's going to have a major impact on that type of industry. So can't say I have too much of a background on that.
Okay. All right, and then we got
but I'm sure those manufacturers are looking at that.
Absolutely. All right, this one is from Fahad. He said, for the Honeywell Eclipse Bordometric used in industrial application up to 125 million BTUs per hour. What percentage hydrogen can be mixed comfortably without modification to the burner design? And also, is there any high percent mix of hydrogen and natural gas with slight modifications? And in that case, can we do that, or can that go? So yeah, on the Bordometric, is that one of those burners that is good as is with the nozzle design, or are they limited based on that design and would need to change the design if they wanted to go full hydrogen?
Yeah. So the design of that Bordometric is very much it's pretty much a tornado in that burner, right? So it's very high spin. Right now, we haven't done any major testing on the Bordometric, especially the large ones, because it takes a lot of hydrogen. So we're still building our substructures to deliver more and more hydrogen to test our bigger burners in all our facilities around the world. The Bordometric right now, we feel comfortable about a maximum of 30% hydrogen. After that, we think we're going to have trouble in the long run with overheating components and things of that nature. And it's one of those burners that, due to the larger size, and we've had other burners that we've had to concentrate on. It's certainly in discussion. So in the next year or so, we're going to be starting to test those burners to a higher degrees of hydrogen. So right now we're comfortable with the 30%. Higher percentages, we just don't have any test data yet to back up what may be needed to change the design to accommodate higher percentages.
All right.
And just a note was our presentation on those different technologies to improve efficiency and air fuel ratio to drive down those carbon emissions or CO2 emissions by reducing your fuel. This is going to be in steps, right? I mean, a lot of companies want to be carbon neutral by 2035, 2050. And that's going to be in steps, right? So if you proceed and start looking at your systems to improve your efficiencies and how you operate, you can take some of those steps towards it. And even if you're looking at new technologies that, hey, maybe not the hydrogen or a high percentage is available yet, but start looking at technologies that in the future can run on natural gas and either higher percentages or pure hydrogen in the future.
Excellent. I think that's all for the questions. And again, thank you guys, Brian and Todd, for presenting and making yourselves available, as well as everybody attending. And again, if you are watching this as a recording and you have questions, please feel free to email me at ajp@lesman.com. And for any of your combustion or thermal needs, reach out to me. We're happy to help and answer questions. I also encourage you to check out some of the other webinars that we have posted on our website. I have a lot of other interesting combustion topics that you may find of interest, and also keep an eye out as we come out with new webinars on a monthly basis. So make sure that you are checking our website frequently, or if not, you may already be signed up for our emails. We will let you know when we have the next one. So again, I thank you guys all for your time today, and everybody stay safe and have a great day.